Hello everyone, this is video 10.1 looking at lines and angles. So we're starting chapter 10, which is on geometry. I will warn you now, this section of the chapter is pretty much all definitions. Some of these are going to be terms that you probably already know. There may be a few that you don't know. Um, there may be some definitions that are treated in a slightly different way. So this might look like it's really basic and it's really review, but I'm really going to encourage you to pay attention and to make sure that you pick up any little bits and pieces along the way. So let's get started. So we got to start at the very, very beginning. These first three things here: a point, a line, and a plane. Um, there's an important aspect of this that I do want to focus on, and it's the part that's sort of in italics there. So we'll say that a point, well, think of it as a tiny dot without any size or shape. So there's no length, there's no width, there's no height, there's no thickness, there's no nothing. And so it's really weird because when we draw a dot, I mean, we're drawing something that has some amount of size to it. So what we're drawing and what it represents are not exactly going to be the same thing. This is a very tricky point, and we don't probably need to get into a whole ton of detail about this with students, but it is something for you to think about in terms of what this means and in terms of student work. In the same way, we can think of a line as being like an infinitely long piece of string. So the infinitely is already going to be problematic for a lot of students. But it's going to be this long, infinitely long piece of string. And again, this has no thickness. Now, it has length, so we can measure how long it is. So we're going into what we would call one dimension. There's one way in which it can be measured. So we know this string is, infinitely long, or we can cut a piece that's 6 feet long. Well, how thick is it? Well, it's not. How wide is it? It's not. How tall is it? It's not. It just has that one dimension to it. And again, we're using something that is three-dimensional, this piece of string, to represent something that only has one dimension. So this is a little tricky. It's a little complicated. The same thing with the third one here, a plane. And so the book describes it as being like an infinitely large piece of paper. So there's no boundary to it. There's no beginning. There's no end. This keeps going in all possible directions. But it has no thickness. So now we can see that it has two dimensions. If we were to lay that infinitely large piece of paper down on a table, we would see that it's going left and right. It's going toward us and away from us. So it's got those two dimensions, um, but there is no thickness to it. So you'll have to decide how much you want to discuss some of the nuance of this with your students. My suggestion is very little. You're going to have some who may know some of this, because they've heard it from older students or older siblings or their parents or something. But for the most part, to try not to get too mired in the nuance of this. Although it is important to know and it is important to understand. We can also talk about an endpoint, and an endpoint is a terminating point. And let me sort of draw what's going on here. So we've got our line, and we can draw what it looks like. So we've got a line here, and so we can call this line AB. And so here's my line with these 2 points A and B. Now, in this case, this is just a line. It's still going to the left and to the right, and we can see because we have these little arrows here that let us know that it's going to keep going. But now if I chop this off at A and at B, then these 2 points A and B become endpoints, because now this is going to stop at A and it's going to stop at B. That's what we mean by terminating, that it's going to terminate, it's going to stop at those points. Now, if I do that, then this becomes a line segment. This becomes a line segment. So this is part of that line, and it has two endpoints. And if I do the same thing, say I go to A and I go through B like that, then we call this a ray. So we call this a line segment up here, and we call this a ray down here. Now, if I were to do using B as the endpoint and going and continuing through A, that's still array. So array just has to have one endpoint, and so in this case, we chose A to be the endpoint, but we could have chosen B to be the endpoint. It doesn't really change anything. So starting with a line, and then taking these 2 points, and if they're both endpoints, that creates a segment, and if only one is an endpoint, then that creates array. So it's really important that we understand the difference between a line segment, and array, because they're used for different things, really. We also have an angle. Now, an angle, the book makes the distinction that we can think about an angle as two different things. And one way we can think about an angle is the amount of rotation around a fixed point. And so if I have here a point, and we'll call this point P, P for point, and then I'm going to come over here and I'm going to make this ray, and I'm going to come over here and make this ray. So I've got this ray PQ and I got this ray PR. And so I could think about if I were to take PQ and rotate it, or if I were to take PR and rotate it. Now, we're not going to get too far into positive or negative or the directionality of this right now. We will in a couple of slides. But right now we can see just the basic idea of moving one to the other. And that's going to create some amount of distance, and that's going to create an angle. If you really want to be specific about it, we're creating an angular distance, not a linear distance, because it's a little bit different, but we'll separate that out here in a moment. So we can think about just this amount of rotation, rotating something around this point P. Now, the other definition is probably what I think of more as an angle, and this is the region between two parts of a line or two lines. So, here we've drawn them as a ray, and a lot of times they're shown as a ray, but we'll see problems where we're looking at an angle between two line segments or between even two lines. So, either one is possible, although I feel like it's most often shown as a ray. So in this case, we're talking about this here, this region that's in between. And it's maybe not the best way to think about it, because when we think of this region, we're thinking of it as an area, and an area usually has squared units. So we think about like a room having square feet, or a city being in square miles. And so this angle is not measured in any kind of square unit. So, maybe thinking about it as a region is not the best way for me to think about it, but this is what I think of as an angle. I think of it as how much stuff is between these two lines, or these two line segments, or these two rays. The point is that both of these are totally valid as ways to think of an angle. So we want to make sure that students are able to understand an angle either as a rotation or as a region. They're both going to work. So when we start to measure out an angle, we're going to use this thing down here, a protractor, and we'll look at this a little bit more as we go on. But the measurement that we're going to use in this class is going to be degrees. Some of you may have seen other ways of measuring angles. You may have worked with radians in the past. We're not going to talk about that at all in this class. We're just going to talk about this as degrees. And a circle, a full circle, is defined as being 360 degrees. So if I were to take half of that circle, so here's my full circle, and that's 360 degrees. If I chop that in half, then I get what's called a straight angle, which is 180 degrees. So the full circle was 360. This part is just going to be half. So that's my 180 right there. So this is my 180. Very small. Again, we can think of this either as this rotation. The 360 degrees would be a full rotation, and then 180 degrees would be just half of that. It would be a half rotation. It always makes me chuckle when people talk about we really turned it around. We turned things around 360 degrees. Like, you went right back to where you were. Really, if you turn things around, you should do a 180 degree, not a 360 degree turn. I got to remember to put my degree symbol here so we know what my units are. And then we could do something like a quarter of a circle, like down here. And this is going to be 90 degrees. And so that's going to be my quarter circle, which we also call a right angle. So we'll talk more probably about right angles than we do straight angles, but we'll see both certainly over the course of this chapter. We also have these terms here, acute angle and obtuse angle. And an acute angle, I got this protractor here for a reason. So this is my 0 degrees, and this is my 90 degrees. And so now we can see typically we measure these things along this counterclockwise or anti-clockwise direction. And so now once we introduce a protractor, now we have a way of sort of like measuring these angles in a way that makes a little bit more sense. Although, you know, from what I've seen in the book, the direction isn't quite as specific. It's a little more flexible in terms of directionality. But either way, an acute angle is going to be one that measures between 0 and 90. So we would say that this is an acute angle because it's between the 0 and the 90. And then an obtuse angle is one that is between 90 and 180. So this would be obtuse, this would be obtuse, this would be obtuse, this would be acute, and this would be very acute. So these are all acute angles over here. These are all obtuse angles over here. This is my right angle, exactly at 90 degrees, and this is my straight angle here at 180. So make sure you know these different names of the angles is a little bit weird because a right angle and a straight angle are specific angles. They're exactly 90 and exactly 80. And then acute and obtuse are a range of angles. Now, we also have perpendicular, and the book says this is when two lines intersect to form a right angle. And I put an asterisk there because really this could be two lines or line segments or a line and a ray or two rays. It could be any line or part of a line. And so that's why this is in here, or part of a line. And that's going to form a right angle. So this is my line, we'll call it L, so we can just name a line, just give it, you know, one name instead of using the endpoints to define it. So this is my L, and I can call this M, and these are perpendicular because they're going to form a right angle, and a lot of times we show a right angle by putting this little box. And so we put these two little lines here, and it makes like a little square here. And so this is the little symbol that shows this is a right angle, this is perpendicular. So in this case, we would say that L and M are perpendicular to each other. So we would say L and M. And if you want to know, the symbol looks like this, like a upside down T. And the idea being that these two parts of the T, they're perpendicular to each other, so they show something that's perpendicular. I could also do a line over here and make this line N, and it's also going to be perpendicular to L. Now the result of this is that M and N are never going to be able to intersect. They're like railroad tracks running next to each other, so they're never going to be able to hit. And when this is the case, we call those parallel. And the symbol for this is two lines that are parallel. So the symbol for perpendicular are two little line segments that are perpendicular. The symbol for parallel are two little line segments that are parallel to each other. It's also kind of convenient because you know, students have pointed out before that these two things look like the two L's in parallel. So there is something parallel in parallel, which is kind of neat. Anyway, so make sure there's a lot we could get into in terms of parallel. This is a pretty deep rabbit hole we can certainly go into, but we're not going to in this class. Just know there's a little bit more to parallel than we're going to cover in here. Now, we also have supplementary angles and complementary angles. Now, we're going to look at two different ways to think about these, and we'll start with supplementary angles. Now, the book definition says when two angles have measures which add to 180 degrees. So, for example, 130 degrees and 50 degrees make 180 degrees. So these two angles are supplementary to each other. Now, another way to think of that would be if I were to take this line and draw it through here. So really what I have now are two angles. I've got this angle over here, which we can call A, which measures 130 degrees, and I've got this angle over here, B, which measures 50 degrees. So physically, I have an angle and an angle which I can add together and make a straight angle. So it's not just a numerical relationship, but it's also a physical relationship. And I can take a piece of paper like this and just sort of rip it like that and get two separate pieces of paper. And then this is going to be my angle A and this would be my angle B. And the idea is when I put those two pieces of paper back together, I still form this straight angle here. I still get my 180 degrees. So it's not just, like I said, this numerical relationship, there's also a physical relationship that's important to show students. The same thing is true for complementary angles. They add up to 90 degrees, so the same thing is going to be true, but I'll do this in blue real quick. So if I drop this down in blue, now this forms a 50 degree and a 40 degree angle, and now these are complementary. They go to make this right angle, this 90 degree angle. So yeah, it's also been pointed out in the past, I'll switch back to red, supplementary has two P's, complementary has one P. And so supplementary, because it has two P's, it's going to make twice as much as complementary. Yeah. I mean, I think it's okay. It assumes that students know how to spell these things with 100% accuracy, but it is a nice way to sort of remember. It's a cute little mnemonic to remember the difference between supplementary and complementary. Three terms here, more to define. We have this idea of a postulate or an axiom. Now, a postulate or axiom is something that we just assume to be true. There are some postulates or axioms which later on we can change or throw out completely and then see how geometry sort of changes. We're not doing any of that in this class. We're going to be dealing with the same postulates and axioms the entire time. So these are things that we just assume to be true. If you go back to that second slide, what we think of as a point is an axiom. It's a postulate. I'll use one term. The book uses postulate. I tend to use axiom, but I'll just stick with the one term. So what a point is, we can't prove. We just assume that there's a thing called a point and it looks like this and it does that. And we assume there's a thing called a line and it looks like this and it does that. And we can assume there's a thing called a plane. So we just assume these things to be true. If we were to say, okay, there's no more lines, then how do things change? We could certainly get rid of that. It'd be kind of silly. It'd make this class a lot shorter. So we're not going to do any of that. We assume these things to be true. Now, we compare this to a theorem. A theorem is something which we have to prove to be true. It might be something that we guess or hypothesize or that we observe, but we're not sure if it's true, and we can't assume it because it depends on other things. So a very famous example that most people have heard of is the Pythagorean theorem. I mean, it says theorem right there in the name. We don't assume the Pythagorean theorem to be true. It's something that has to be derived from something. It has to be shown or proven to be true. So that's the difference between a postulate and a theorem. The process by which we show these things to be true or not is called a proof. And we'll talk a little bit about proofs in this class. I also want to point out there's some other terms that you may have heard when you took geometry before, like corollaries or lemmas and things like that. We're not dealing with any of that in here. Pretty much everything is going to fall into one of two categories. Either it's a postulate / axiom, it's a thing we assume, or it's a theorem, which is something we're going to prove. We're not going to get too far into other forms of provable statements. So, but we will look at some things that are proofs and talk about sort of the nature of proof a little bit. So just to give an idea of a proof, so we've got here this little figure, and we've got AC, CD, and DE are line segments that are all the same length. And then we want to prove that AD, this length, is the same as this length. So we're not going to go through the proof. I just wanted to give an idea of what a proof sort of like looks like. We have to be told some things. We have to be given some conditions or some figures that we're going to be working with. And so we usually call these the givens of our statement. So I know this much is true. There's three line segments, A, C, C, D, D, E, and they're all the same length. And a lot of times we'll be given a figure so we can kind of see how they all sort of relate to each other. And so this is important because we can see that A, C, D, and E are all in the same ray. So they're all collinear. And then we've got here a statement that we want to prove. We want to show that this length is the same as this length. Um, so we're going to do some very basic proofs in this class and the manner in which we'll talk about a little bit more as we get closer to them. A common type of problem in dealing with proofs in geometry deals with figures like this one over here to the right. This line L, M, and N, which is very similar to the figure I drew a moment ago, except you can see that L and N are not perpendicular, M and N are not perpendicular, but L and M are parallel. So this is really important that we're dealing with L and M are parallel to each other. So when we have two parallel lines and a line kind of cutting through them like that, if it's perpendicular or not, the line that cuts through the two parallel is called a transversal. And so it's a line that's shown to be crossing two parallel lines. Now, there's a whole bunch of different relationships that are created in this situation, and the book really only focuses on two. So the first one that the book focuses on is this idea of corresponding angles. Corresponding angles are angles that are in the same position in relation to the parallel lines in the transversal. So what I mean by that is, if I look at angle 1 and angle 5, so they're both in the upper left. They're both in this position in relation to the parallel line and the transversal. So one way to think about it would be if you moved L and slid it down to where it was on top of M, 1 and 5 would be in the exact same position. 1 and 5 would both be in that upper left position. So we would say that 1 and 5 are corresponding. So 1 and 5. We'd also see that 4 and 8 would be corresponding. We can see that 3 and 7 would be corresponding. And we can see that 2 and 6 would be corresponding. And so we can kind of see upper left, upper right, lower left, lower right. We can kind of see the position where they are. Now, corresponding angles are always congruent. And we can kind of see the congruency because, like I said, if we were to take 1 and slide it down to where it was on top of 5, they would match up perfectly. So the transversal would be in the same spot. The parallel lines are parallel, so they're in the same spot. So it creates that same region if we think about that initial way of thinking about angles. So we can see how these are all congruent. I'll switch to blue. We also have alternate interior angles. Now, the alternate means that they are on opposite sides of the transversal. So alternate relates to this. And then I'll do this in green. The interior means they are between the parallel lines. So we've got two different terms that sort of mean two different things. The alternate deals with what side of the transversal. The interior deals with whether or not we're inside, outside the parallel lines. And so we can see here, I'll switch back to blue here, the 4 and the 5 would be alternate interior angles. So 4 and 5 are alternate interior angles. And so would 3 and 6. Not to leave them out. Now, 4 and 6 are both interior, but they're not alternate. And then you've got 2 and 7, which are alternate, but they're not interior. We're not dealing with any other cases. These are the only two cases we're going to look at in this section, corresponding and alternate interior. Again, if you remember your high school geometry even a little bit, you remember there being all the same side interior, alternate exterior, all that. We're not doing any of that right now. So these are the only two that we're going to focus on in this case. And again, both of these cases are going to produce congruent angles. We can see that 4 and 5 are congruent, 3 and 6 are congruent, they're alternate interior, and then all the corresponding pairs are congruent as well. We also have, and this makes it a little confusing because we also have interior, exterior angles in relation to a triangle. So depending on the context, depending on the type of problem, Interior and exterior are gonna mean slightly different things. So they could be angles could be interior, exterior to the parallel lines or to a triangle. An interior angle to a triangle is going to be the angle that is inside this triangle, like here. And so we'll call this angle A, just so it has a name. And now the exterior angles are going to be these that are supplementary to the interior angle. And so you can see that A and 1 are supplementary. And you can see that because they form this straight angle here. They form this straight line. Now we can also see, I'm going to undo that because I made that line a little bit bigger than I wanted it to be. So now we can also see that A and 2 are supplementary. And so now we can see over here, and they form this straight angle. And so 1 is exterior to the triangle, and 2 is exterior to the triangle, but this angle is not. And that's because this angle here, the angle, we'll just call it no, angle no is not supplementary to A. It doesn't form a straight angle to A. Some of you who have seen this sort of thing before might recognize that A and no are actually what we call vertical angles, and they're actually going to be congruent to each other. So these are congruent, they're vertical or opposite angles to each other. And so those are actually going to be congruent. Yeah, so this is one way to recognize interior, exterior, and then also an example we can see here of vertical angles. I know this is a lot of terms, a lot of definitions. Like I said, hopefully at least most of this is familiar. We're going to need a lot of these terms and a lot of these definitions. The next section is impossibly short. So really what I want you to focus on for this section is making sure that you know these definitions inside out. We're going to need them for the rest of chapter 10 and really the rest of chapter 11 and the rest of the semester. So make sure that you know these terms and definitions. The ones that you already know, set them aside. Don't spend a lot of time learning what you already know. Make sure you identify the terms that you don't know, practice them, see how they can be used, make sure that that you're able to fully understand what those terms mean, and if you have any questions, make sure you bring them to class. So, your checkpoint problem. Take 3 straight lines. Is there a way to make them intersect at just 1 point? Is there a way to make them intersect at 2 points, 3 points, 4 points? What's the most number of points you can make those 3 lines intersect? Can you make 3 lines intersect at 12 different points, at 15 points, at 20 points? What's the most? And then what's the fewest number of points you can make those 3 lines intersect at? So I'll leave this problem for you to think about. If you have any questions about this problem or anything else from the video, please bring it to class and we'll get your questions answered. All right, thanks.